Good afternoon. Today I'm going to show you the different methods for solving limiting reactant problems. Let's start by identifying the key parts of our chemical reaction. Up until now, we have assumed that the perfect amounts of each reactant are going to react together. However, this normally does not happen for a variety of reasons. The limiting reagent is the substance that is completely used up, meaning that there would be none left at the end of the reaction. The excess reagent is the substance that is not completely reacted, meaning that there will be some left after the reaction is complete. There are three different methods you can use to solve these problems. I'm going to use this example to illustrate each method. In each case, the first step will always be to convert your given amount into moles. For method number one, you will start by converting one of your reactants into the other. If completely using up one reactant requires more than is present for the other reactant, that reactant will be in excess. If the amount needed for the second reactant is less than what is present, then that reactant will be the limiting reactant. So let's look at an example to show you how this works. So the first step in any type of stoichiometry problem is to get our balanced equation set up. So for this reaction between hydrogen and oxygen to produce water, I will have the following balanced equation. 2H2 plus O2 forms 2H2O. Now, for this method, the first thing that we can do is choose one or the other reactant. It does not matter which one, so I'm going to arbitrarily choose the hydrogen for this. So I'm going to start by converting my grams of hydrogen into grams of oxygen. So I would take the 1.05 grams of the H2, and I'm going to start by dividing by its molar mass, which for hydrogen is 2.02. And then next I will do my mole ratio. So I would have 2 moles of hydrogen for every 1 mole of oxygen. And then lastly, converting it into the same unit as the oxygen given in the problem, I'll take 1 mole of the oxygen and 32 grams for the oxygen. So when we calculate this out, to completely use up all 1.05 grams of the hydrogen, it would require 8.32 grams of oxygen. Since we only have 1.22 grams of oxygen available, that will tell us that the oxygen will now be our limiting reactant. Okay, for method number two, you will take the amount of each reactant that is given and convert it into one of the products. If it doesn't specifically tell you to calculate a specific unit for the product, just solve for moles. It's the easiest thing to do. Whichever reactant will then produce the smallest number of moles of the product will be your limiting reactant. Let's now look at that same example. So once again, we had 2H2 plus O2 reacting to form 2H2O. We started with 1.05 grams of hydrogen, so now we're going to convert this into grams or moles of water. So once again, start by using my molar mass, 1 mole, 2.02 grams of the hydrogen, and then mole ratio. In this case, I would have 2 moles of H2 producing 2 moles of water, and then we can solve for that. The amount of water that would be produced would be 0.520 moles. We're now going to do the same thing with the starting amount of oxygen from the problem, which was 1.22 grams of O2. I would then convert using my molar mass into moles, so I'd have 32.00 grams of O2, and then my mole ratio in this case, I would have 1 mole of oxygen producing 2 moles of the H2O. And when I convert that, I would end up with 0.076 moles of H2O. Now, since the amount of moles from the H2O, for the H2O coming from the oxygen is smaller than it is for the amount coming from the hydrogen, I would know that O2 will be my limiting reactant. Method 3 is by far the most advanced but also the most powerful tool that we can use to solve a limiting reactant problem. This is called the Rice table method. Now, what the Rice table stands for, the R is just your balanced chemical reaction, the I is your initial amount of moles, the C is your change in coefficients, and then the E is your ending amount. For this method, the first thing that you will do is you will convert the amount of each reactant into moles. That is your I. Then we would set it up and divide that initial amount of moles by the coefficient, which would represent the molar ratio, and that will get us to the moles of equivalence. This will allow us to compare the values for moles of each reactant on an X to X basis. And then based on whichever reactant gives you the smallest value for X, that will be your limiting, and then you will convert that amount into whatever product you were asked to solve for. I'm going to begin this third method illustration by going back and showing you the normal stoichiometric way that we would solve this problem, and then breaking down each individual piece into the Rice table. So once again, we started with 2H2 plus O2 forming 2H2O. We had 1.05 grams of the hydrogen, and we converted that into moles by dividing by its molar mass. This step right here, that would be what we would do for the I on our chart. For the next part, where we have our molar ratio, we would begin by dividing by the coefficient for the hydrogen gas. That part right here is where we will use the C on our chart. And then finally, once we would solve for the moles of water, if we were asked to convert to grams, we could convert the moles of water into grams of water by multiplying it by 18.02 grams. So this would be the ending amount that we would see over here. Now, as we begin this process, again, the key is to stay organized within our chart. So I'm going to rewrite this, and I'm going to leave plenty of space so that we have room to work. So here's my R, my balanced chemical equation. For my I would take the 1.05 grams of the hydrogen, and I would divide it by the 2.02 grams of hydrogen, and that's going to equal 0.520 moles of hydrogen. We also had 1.22 grams of oxygen, and we're going to divide that by the molar mass, 32 grams, and when we solve that, we end up with 0.038 moles of oxygen. So throughout this process, that will be my I, just converting it into moles. And then for my C, I have a coefficient of 2 for the hydrogen, and the reaction is always going to consume our reactants, so I'm going to put a minus 2x here, the 2 again being the coefficient, the minus sign just telling us that is going to be consumed. For the oxygen, because it has a coefficient of 1, I would just place that with a minus x. And then finally, for the water that will be produced, because we're now going to increase that amount, it'll be a positive 2x. Now, at this point, all we have is a simple math equation to solve for x. So for each one of my reactants, I'm going to simply take the initial amount of moles that I have, and I would set that up as the minus 2x for the hydrogen or the minus x for the oxygen. And because we're trying to see which one would be limiting, I'm going to set that equal to 0 to assume that it would be completely consumed. So now, solving for my equation, I'd have 0.520 equals 2x. So my x would equal 0.260 moles. When I do for the oxygen, the same thing. I'd have 0.038 minus x equals 0. So my x would equal 0.038 moles. Now, since the 0.038 moles is the smaller of my two amounts for x, I know that the oxygen will be my limiting reactant. So now, to solve for the water, all I would then do is take 2 times the 0.038 for my value of x, and then I could multiply that by the molar ratio, or sorry, the molar mass, and I would have 1 mole of the water, 18.02 grams of the water. And when we solve for that, we would end up with 1.37 grams of water. Okay, so for this first example problem, I'm going to show you using method 1 how we would solve this problem. So once again, how many grams of water are producing the oxidation of 1 gram of glucose, C6H12O6, with 0.50 grams of oxygen gas? Now, with method 1, once again, we're going to convert one of our reactants into the same unit as our second reactant. So for this problem, I'm going to go ahead and convert the grams of oxygen gas into glucose. So the first step in this process, I would take the 0.50 grams of the O2 and I would divide by its molar mass. So I divide once again by 32.00 grams. And then I now have my molar ratio, so I would take 6 moles of oxygen for every 1 mole of glucose, C6H12O6. And then for the last step, I'm going to convert the moles of glucose into grams of glucose, since that is what our other reactant is listed in. So when I do the math for this, you end up with 0.469 grams of glucose. Now, what that means is that to completely use up the 0.50 grams of oxygen, it would require 0.469 grams of glucose. However, since we have 1 gram of glucose available, I have more than enough glucose to completely use up all the oxygen. So in this case, we would have oxygen as our limiting reactant. Now, to solve this problem, once we now know the limiting reactant, we can then go and solve for the grams of water. So I could take the 0.50 grams of the O2 and I can convert that into moles. And now use the mole ratio between the oxygen and the water. And then finally, since it's asking for grams of water, I can use the molar mass, 18.02, to convert that into water. Now, for your final amount, we would have 0.5. We'd end up with 0.282 grams of water. Now, as an example of method number 2, we're going to solve for the mass of PCl3 formed in the reaction between 75 grams of phosphorus and 275 grams of chlorine gas. So once again, the first thing we need to do is come up with a correctly balanced equation. So we would have P4 plus 6Cl2 forms 4 PCl3. Now, we have 75 grams of the P4, so the second method, if you recall, we are going to take each of our beginning amounts and we are going to convert them into the product. And then whichever one produces the smallest amount of product will be your limiting reactant. So in this case, instead of solving for moles, because the question is asking for the mass, I'm going to solve for the mass of PCl3. So we have 75 grams of the P4. The molar mass, 1 mole of the P4, is going to be 123.88 grams. We now have a 1 mole of P4 to 4 moles of PCl3. for the molar ratio. And then finally, 1 mole of PCl3 will be 137.32 grams of PCl3. So when we solve that, you end up with 333 grams of the PCl3 being produced. When we take the 275 grams of the Cl2 and convert that into the PCl3, we would start by dividing by the molar mass of chlorine gas, 70.90, and then we have our mole ratio, 6 moles of chlorine for every 4 moles of the PCl3, and then the last step again will be the 137.32 grams of PCl3 for every 1 mole of the PCl3. And when we solve that, you end up with 355 grams of PCl3. Now, since the 75 grams of the P4 produce the smallest mass of the PCl3, we know that will be our limiting reactant, and what we would have for the Cl2 would be the excess. For our last reaction, I'm going to show you the Rice table method using the reaction between cyclohexane and oxygen to produce adipic acid. Adipic acid is one of the main components in the commercial production of nylon. We're going to assume that for this reaction we're going to have 25 grams of cyclohexane reacting with 25 grams of oxygen gas. And based on that reaction, we're going to determine the theoretical yield of the adipic acid. Now hopefully you remember from our percent yield conversation earlier that the theoretical yield for a reaction is the maximum amount of the product that could be produced from the given reactants. In part B, based off of a lab collected 33.5 grams of the adipic acid, we are going to determine what the percent yield would be for this reaction. And then part C, we are going to determine the number of grams of the excess reagent left after the reaction is complete. In order to be able to have this all out on one page, we're going to transition all of the work onto the next slide. Okay, so once again I'm going to set up the Rice table here, and I'm going to try to leave myself plenty of space. So I have 2C6H12 that is going to react with 5O2, and it is going to produce 2H2C6H8O4 plus 2H2O. So once again, we are starting off with 25 grams of each of our reactants. So here's my R. For my I would take the 25 grams, and I'm going to divide it by the molar mass of the cyclohexane, which is 84.18 grams per mole, and that's going to leave me with 0.297 moles of the cyclohexane. For the oxygen, we start off once more with 25 grams. Going to divide that by the 32.00 grams per mole, and that will leave us with 0.781 moles of oxygen. So now, our C, once again, we are subtracting our coefficients. So I'd have minus 2x, and I'd have minus 5x. I would have plus 2x for the adipic acid and plus 2x for the water. Now, to solve for x once more, I'm setting up my math equation. So I would have 0.297 minus 2x equals 0. So in this case, my x should equal approximately 0.149 moles. For the oxygen, I would have 0.781 moles minus 5x equals 0. So in this case, my x would equal 0.156 when I plug that in and solve. In this instance, you can see that the 0.149 moles is smaller than the 0.156, so the cyclohexane will be my limiting reactant, and the oxygen will be my excess. So to solve for this problem, I would then take my value for X and multiply that by 2 for the adipic acid. So I'd have 2 times the 0.149 moles. And then I would simply multiply that by its molar mass, which is 146.14 grams per mole. And when I solve that, I end up with 43.4 grams of the H2C6H8O4. So that would be my theoretical yield. Now, just as an aside, it makes this method really useful if it asks you to solve for an excess reactant. Because I know what my value for X is, I could simply subtract off the 0.149, and that would tell me how much I would have left over of the oxygen. So I'll come back and work that out in just a second so you can see it. To finish the part B for this problem, where it gave us 33.5 grams that were actually produced from this reaction, I would then take that actual yield and I would divide it by the theoretical yield that we just calculated, 43.4, and I would multiply that by 100%, which would equal 77.2% overall. Now, as I was saying, what makes it really nice if it is asking you to also solve for an excess reactant, so let's just kind of pop that on here as C, find the amount in excess. What I could then do, since I know that my X is equal to 0.149, I could then, for the oxygen, knowing that I started with 0.781 moles, I could subtract 5 times the 0.149, and that would equal 0.745. So if I took 0.781 moles and I subtracted the 0.745, that would leave me with 0.036 moles of oxygen left over, and we could then multiply that by the molar mass of oxygen to solve for the number of grams. So if I took that and multiplied it by the 32 for the grams of oxygen, you would end up being somewhere approximately around 1.1 grams of O2 that would be left. Okay, this wraps up the recording for limiting reactants. Hopefully this helps. Please come to class tomorrow with questions. Thank you.